We'll walk you through an in-depth analysis of IoT protocols, their real-world applications, vulnerabilities, and strategies to secure them using effective threat modeling. This presentation will follow a structured approach. First, I will discuss 4 IoT protocols. Next, we will explore their real-world applications and analyze a specific attack scenario. Finally, I will model a man-in-the-middle attack. First, we will talk about 4 common protocols. They are Bluetooth, Wi-Fi, MQTT, and Co-op. Bluetooth is a widely used wireless communication protocol designed for short-range data transfer. It operates in the 2.5 GHz ISM band. It is primarily used for D2D communication and to connect IoT devices to a local hub, which can act as a gateway to the cloud. Its simplicity and widespread adoption have made it a cornerstone technology in the IoT ecosystems. We can see from the picture that Bluetooth is located in the device layer. There are 5 versions of Bluetooth, where version 1 to 3 are older versions, while version 4 to 5 are known as Bluetooth Low Energy. Wi-Fi is a widely used wireless communication protocol in IoT, known for its high data rates and compatibility with Internet-based applications. It operates in the 2.5 GHz and 5 GHz frequency bands and connects IoT devices directly to a local area network or Internet gateway. Recent advancements, such as Wi-Fi 6 and Wi-Fi Hello, have further enhanced its suitability for IoT by optimizing power efficiency and extend range for low-power devices. Yes, we can see that Wi-Fi is also located in the device layer. These are the similarities and differences between Bluetooth and Wi-Fi. MQTT is an application layer messaging protocol designed for low bandwidth, high latency, or unreliable networks, making it an excellent fit for IoT. It uses a lightweight publishers-subscribe model, where devices publish data to a central broker, and other devices subscribe to receive that data. This enables for efficient and scalable communication among IoT devices. Co-op is another application layout protocol designed for IoT, focusing on resource-constrained environments like sensor network. It is based on the RESTful architecture, allowing devices to communicate using HTTP-like methods while consuming significantly less bandwidth and power. These are some similarities and differences between MQTT and Co-op. Next, we will talk about the real-world applications for these 4 protocols. Bluetooth is widely used for short-range communication in IoT devices. BLE is particularly effective for applications requiring minimal power consumption, such as wearable devices and smartwatches. Wi-Fi is commonly used in smart homes, offices, and industrial environments, enabling devices like smart cameras, voice assistants, and IoT hubs to communicate with the cloud. MQTT is commonly used in scenarios like remote monitoring, home automation, and industrial IoT because it enables real-time data exchange with minimal overhead. A common example would be smart agriculture. Co-op is particularly suited for environments where lightweight communication is crucial, such as smart city applications, environmental monitoring, and healthcare devices. Each protocol has specific strengths suited to different environments. In the third section, I will analyze a specific attack, discussing its impact and what can be done to prevent it. The attack I will be analyzing is Bluebird, a Bluetooth-based cyber attack discovered in 2017. Bluebird targeted vulnerabilities in the Bluetooth protocol stack across various platforms, including Android, iOS, and Linux. What set Bluebird apart from traditional attack is that it doesn't require the targeted device to be paired with the attacker's device or even in discoverable mode. Bluebird attack starts by locating active Bluetooth connection near the attackers. Attackers then send crafted packets to exploit protocol vulnerabilities, gaining control over devices. The attacker first retrieves the device's MAC address, which is a unique identifier for that device. By probing the device, the attacker can determine the victim's operation system and adjust the attack accordingly. Once the vulnerability is identified in the Bluetooth stack of the target platform, the attacker can exclude the exploit to meet their malicious objectives. At this stage, the attacker controls to perform a man-in-the-middle attack and control the device's communication, or take full control over the device for cybercriminal purpose. The bluebird attack is extremely dangerous because it takes advantage of vulnerabilities in blue-enabled devices, which include over 8.2 billion devices worldwide. What makes bluebird so alarming is that it spreads through the air, completely bypassing traditional network defenses. It doesn't require any user interaction or Bluetooth pairing, making it highly contagious, as it's moved effortlessly from device to device, even in secure air-gapped networks. At the same time, hackers can near total control over the affected devices. This is because Bluetooth provides a high-level access across operating systems. The consequences are serious. Bluetooth can serve any malicious objectives, from smartphones and computers to IoT devices like TVs, cars, and medical equipment. The range of potential targets is staggering. With its stealth nature and potential for massive damage, Bluebird is one of the most significant cybersecurity threats in recent years. Since the consequences are so severe, how can we prevent it? As consumers, we can disable Bluetooth when it's not in use to minimize exposure to potential attacks and regularly update our device with the latest security patches. Many operating systems have released patches specifically addressing Bluebird vulnerabilities. For long-term security, the adoption of distance bonding protocols and binary encryption is essential. Manufacturers have learned that prioritizing security in protocol design is crucial to preventing such signal exploits. The Bluebird incident highlighted critical flaws in Bluebird's convenience-first design. Security improvements since then include cryptographic enhancement and stricter device validation. It also underscores the importance of keeping IoT devices updated to avoid large-scale vulnerabilities in the future. Lastly, I have utilized a hybrid approach by integrating this threat framework and the attack tree methodology to model a man-in-the-middle attack. A man-in-the-middle attack is one where an attacker secretly intercepts or manipulates communication between two parties without their knowledge. This is common in IoT environments, where attackers can exploit unencrypted or vulnerable communication channels to access sensitive data or inject harmful content. Threat provides a framework to classify and analyze potential security threats. It stands for spoofing, tampering, repudiation, information disclosure, denial of service, and elevation of privilege. These are the definitions for this sixth threat. The attack tree methodology is a powerful tool for visualizing how an attacker might achieve their goal. It starts with a root node representing the main objective and branches out into the possible methods and steps an attacker could use. These branches provide a structured way to understand and prototype potential threats. This hybrid model combines the threat framework with the attack tree methodology, focusing on interacting between key components like the smart thermostat, router, and MQTT broker. The arrows represent the attack flow, highlighting threats such as spoofing, information disclosure, and tools, as well as the sequence of vulnerabilities exploited in a man-in-the-middle attack. The attack begins with the attacker exploiting vulnerabilities in the network. The first step involves ARP spoofing, where the attacker sends fraudulent ARP messages to thermostat to corrupt MAC IP mappings. This leads to a reputation threat, as the attacker impersonates trusted device to establish a foothold in the network, allowing the attacker to intercept communication between thermostat and the router. Once ERP spoofing is successful, the attacker moves to intercept network packets, exposing sensitive data such as IoT device credentials and commands, which is the information disclosure threat. Using the intercepted packets, the attacker injects malicious commands, leading to an EOP threat. This allows them to manipulate device behavior or compromise the MQTT broker, gaining control over connected IoT devices. Alternate attacker paths that start with the Wi-Fi network, where the attacker exploits vulnerabilities to spoof router credentials or manipulate network traffic. This creates another spoofing threat, enabling tamper with device, intercepting sensitive data, or overloading the MQTT broker to cause the doors. The smart thermostat is particularly vulnerable to tampering threats, such as firmware modification or data extraction. Similarly, the MQTT broker is also a high-value target for privilege escalation. Once compromised, the broker allows the attacker to send unauthorized commands to the thermostat or overwhelm the broker with requests, disrupting its functionality. For the attack vector, the attacker uses ARP spoofing to deceive the smart thermostat and router, intercepting their communication. By positioning themselves as an intermediary, the attacker can eavesdrop on data and inject malicious commands, such as altering temperature settings or disrupting device functionality. For attack paths, the attack begins with ARP spoofing to establish control over the communication channel. Next, the attacker intercepts data packets exchanged between the thermostat and the router. Finally, the attacker injects malicious commands to manipulate the thermostat or escalate their control over the system. The key attack surfaces are the smart thermostat, Wi-Fi network, router, and MQTT broker. Weak security configuration or outdated protocols in any of these components provide the attacker opportunities to exploit vulnerabilities and compromise the system. There are three possible threat scenarios caused by man-in-the-middle attack. First, data manipulation is a significant risk. An attacker could alter temperature setting or modify usage logs. Next, eavesdropping is another potential threat. By intercepting network traffic, the attacker can gain access to sensitive data, such as user credential or personal settings, compromising both privacy and security. Lastly, credential hijacking poses a severe threat. By stealing authentication data, attackers could gain unauthorized access to not only the thermostat but also other connected IoT systems, potentially escalating the attack's scope. These three scenarios illustrate the high stakes of securing IoT devices and the networks they operate on. In conclusion, while IoT protocols drive innovation, robust security measures like encryption, secure authentication, and monitoring are crucial to protect connected systems and ensure user trust. Thank you for listening to my presentation. If you have any questions or thoughts, please feel free to share them in the comments below.